Hey guys, this is Daniel Hayes. I've been working on Lab 1 and I think I finally got it figured out. So I decided to put together a tutorial on how to blink an LED without libraries, just using bit shifts, masks, and using the memory addresses themselves for the microcontroller. Um, so the first thing we want to do to get started is we want to open Code Composer. I've already got it open here. I've already got my program here. So to start a new project, we can go File, New, CCS Project. Here you can put in your input, or target rather, and TIVA C series. It's the 123GH6PM. For connection, we're going to do Stellaris in circuit bug interface, even though we're not going to be using it for this. And then you can just select an empty project with main.c. Okay, I'm not going to create it because I already have. I renamed main to be blink.c. You can pretty much rename it to anything you want. I named my project Lab 1. So let's get started here. So the very first thing you want to do to get this thing to work is you want to enable the clock, the system clock for whichever port that you're using. So looking at the manuals, let's go to the evaluation board manual and not the microcontroller manual. We can see that the onboard LEDs, it's a RGB LED, and it's red, blue, and green, are PF1, 2, and 3. And what that means is it uses port F, and that's pin 1, 2, and 3 of port F. And later on we might use the switches in the lab for controlling the LEDs, but we're not going to use them in this tutorial. So I know that I want to use port F. So the first thing I want to do is I want to figure out how to enable the clock for port F. And so what I did is I went to the microcontroller manual, and I found it online, and it's like 1,400 pages long. So what I did is I just did a Control F and did a search of the PDF, and I found stuff about the clock. Here on page 464, we can see that run mode clock gating control register 2. This register controls the clock gating logic in normal run mode. Each bit controls a clock enabled for a given interface function or module. If set, the module receives a clock and functions. Otherwise, the module is unclocked and disabled, saving power. I've read through this a little bit, and there's a RGB as well. But something about legacy software, they recommend using the GC2, so that's what we're going to do. And what we want to note here, first of all, is we want to see that this is an offset of hexadecimal 108. Okay, so that's going to be our offset to find the register to set this is enabled. And the offset is in reference to the base address of our system control. So I'm in the system control section. So if I come down here and I can see the system control register, and it's this is a 32-bit processor, so each register is 32 bits wide, and I can see right here that the base for RCGC2 is hexadecimal 400FE000, and the offset is 108, like we just said. So that means that the register that we want to write to enable the clock is this base address plus the offset. So the actual address of this register is 400FE108. So 000 hexadecimal plus 108 is just, you just put the 108 in those 3 digits. So the address for this register is, like I said, E108. Now if we look at what we got here, we see these reserved bits, and the RO means read only in certain circumstances. Reset equals 0. Anyways, the reserved bits, we don't want to mess with any of those. And if we look here at the lower bits, we can see GPIO A, B, C, D, E, F. So if we're using the onboard LEDs, we want to use GPIO F because that's the pins that it's hardwired to. So this is the bit we want to enable to get a clock to the GPIO F. So if we look at our bits, we got 0, 1, 2, 3, 4, 5. So it's the 6th bit, which is bit 5, because we're base 0. And so we want to put a 1 here, 0, 0, 0, 0, and 0, because we're not using any of the other GPIOs right now. So I need 1, 0, 0, 0, 0, and we can use binary, but hexadecimal is a little more succinct. It's a little bit easier to read sometimes when you're programming. So I've got my calculator and I've put it into programmer mode. And so I'm going to go to binary. I'm going to clear this up, and I want 1, 1, 2, 3, 4, 5. Nope, that's too many. 4. 1, 2, 3, 4, 5. Yeah, one more. This is the number I want to put right to that register, because I want a 1 in that 6th bit, which is bit 5. And once I put that in there, I see that that in hexadecimal is 20. So when we write to this register, we're going to write hexadecimal 20 to this register to get a 1 right here. All right. The next thing we want to do is we want to set direction, and that's like tell the pin, is it an input or output? And step 3 is going to set the pin as a digital, enable it as a digital pin, so high or low, and that's it. So let's start looking at our code here, see what we got. So the first thing I'm going to do is do my definitions here at the top of my program, and we just talked about the system control clock. And so we got an offset of 108, and what we're going to write to that to enable port F clock is hexadecimal 20, which is what the calculation we just did. Now this line here is a little confusing, so let's look at what we got here. So our register that we want to write to is that base register plus 108, so that's what's here. This is the register we're going to write to. And this part right here, the brackets with the asterisk, so we're typecasting this number. The program doesn't know what this is. It just sees it as a unsigned long int, I believe. So we're going to typecast it, and that's what we're doing right here. So we're going to say it's volatile unsigned long, and it's an unsigned long pointer is what we're saying here. And let's see here. The reason why we want an unsigned long is because a long type is 32 bits. And our registers are 32 bits wide, so that's why we're using the long. And the other asterisk right here is dereferencing this right here. It's saying that we don't want this actual number, we want what is at this memory location. So I know this line is a little confusing to look at, but just bear with me that we're typecasting this as a pointer address, and say we want what's at this memory address when we call this variable. Alright, so we've got through that. That's going to set our clock. Let's see, GPIO F registers. So the first line here, we're going to define port F dir. And one thing I want to say about, I've named it port F because one, that helps me when I look back in my code and say, oh, this is port F, not port A or port B, so I don't get confused. But you can name this part right here anything you want. Just something that's memorable, and when you come back and read your code, you understand what you've done. And comments helps a lot. So port FDIR, what is that? That's offset of data direction register is 400. So this is the data direction register. And what I said, that was step 2, and set the direction. And what that means is this pin going to be an input or an output? So we're setting the direction of this pin. So I've got a reference here to the manual. It's page 663. So I'm going to come here. I'm going to go to 663 and GPIO DIR, setting a bit, and the register configures the corresponding input to be an output. So if it's clear, if it's a 0, that means it's an input. If it's a 1, it's an output. So we're outputting a high signal to our LED, so obviously we want to put a 1 in the correct location. And our offset is hexadecimal 400. And so the manual is telling us that we have to offset 400 from the base to get to this register that we want to write to. So we come down here to GPIO-F. So the AHB, that's Advanced High Performance Bus. And then we have the APB, which is the Advanced Peripheral Bus. Wow, that's hard to say. I tried to use the high performance one first, and it didn't work, and I'm not sure why. According to the diagram, they're both connected to port F, so I'm not sure why it didn't work. So I just went ahead and just used the APB, and its base is 4002 5000 in hexadecimal. So to get to this register that we want to write to, we need to add our offset to this base, and that gives us the exact address of this register. And it looks like we've got 8 bits that we can write to. And so this should be PF0, PF1, PF2, and so on and so forth. So back to the code. We can see here, this is our base plus the offset. You can see the 400 there. Same convention as up here. And also, I forgot to mention the volatile part. I found out that the volatile part of the typecasting keeps some optimizations from the compiler from running. That helps out with this low-level stuff. I don't fully understand exactly why, but I just know that they say to use the volatile keyword there. So we got our address here, and we're going to define it as our direction. Okay, and that's all we need so far. Next step is to enable the pins that we need, and this is 682. Back to the manual. 682. Enter. Okay, digital enable. We can see our offset is hex 51C. Our base is the same for all these, so it's the same one as the one we just did. So we can see that I got 51C offset in our base address, so we've got that defined. And you could use this part right here in the code, but it's just really confusing to look at. So if you define it and put a name on it, it's just a whole lot easier to read your code when we get down to the actual main function. What's next? Data. All right, so I didn't talk about this one earlier, but port F data is basically the actual data that you're going to write to the pins. It it's a method for writing data to a certain port without messing with any of the other pins at any time. This, let's rename that PF1. That's fine. That's fine. Offset data register PF1. So PF1, 2, and 3. That's our red, blue, and green LEDs. Let's see, page 654. Sorry if I'm taking a little bit long to describe this stuff. I'm just kind of doing this off the top of my head here. Data register operation. This goes into a little bit about, it's a little confusing to look at for sure. It took me a while to get through this, but basically it's just saying, you know, you write through here to get your data to your pins. And what was the other page? 662. That's the more important one, I think. Yeah, here we go. Its offset is 0, so we're just going to use our base, which was the 4002, 5000 hexadecimal, and here's our bits that we're going to write to, and what this is PF0, 1, 2, 3, 4, and so on. Here is where I'm going to define basically a binary number for each port pin. So red was, let's see, what was red? Red was PF1. So 1 is the second bit out of the 8 bits of data. So if we want a 1 in the second bit, that's hexadecimal number 2. Just to show you that, let's go to here, go to the hex and clear, and I'm just going to put 2. And we can see here that binary, that's 1, 0. So our second bit has a 1 in it, and that's what we want. Blue is PF2, and that's the third bit. So the third bit, hex, we're going to put in 4. Oops. Oh. Yeah, it was hex 4. Hexadecimal clear 4. And in binary, that's 1, 0, 0. So we can see our 1 is in our third bit. And the 8 is going to put a 1 in our fourth bit, because the green LED is PF3, which is bit 4. So this is basically just putting ones in the correct locations for, and we named them red, blue, and green just so it's easy to understand. You could have easily named these PF1, PF2, and PF3, but red, blue, and green makes a little more sense. Next line, function prototype. This is just to help the compiler understand what's coming up. We got our separate function here for our delay. A delay, we're going to pass in a unsigned long, and void, we're not going to return a value. So we got void main void, we're not passing any variables, we're not returning anything. So this is the meat of the program. So this line here, syscontrol RCG C2. This is our clock enable. So we've defined our clock GPOF as hex 20 because that's the offset we needed. Not really the offset, but the correct hexadecimal number to put a 1 in the correct bit to enable the clock for port F. So we're going to do a OR. So we're going to take whatever's in there now. I think by default it's zeros. So we're going to OR with our hexadecimal 20, and that will put a 1 on port F, so it enables the clock. So that's what we're doing here. Port F dir, bitwise OR with hexadecimal E. Let's check out hexadecimal E. E is 1110. Okay, so that's bits 2, 3, and 4 are all ones, And what that does is we're going to say DIR, so direction is output for both red, green, and blue. So we said this one was the second, third, and fourth bits. So this E is taking care of all three of them at the same time. So set red, blue, green LED pins as outputs. Same thing here. We're going to put them all as, we're going to enable all of them as digital, digital enable. By default, they are tri-state or the high impedance. So now our data, we're going to just initialize our data as all zeros. This is just to make sure that all zeros are in there before we start a program. And this is the actual data where it's writing to turn the LED on or off. Alright, so we got a while one, so this is we're just going to keep looping forever until we stop or cut power to our board. Port F data. So here's the magic. Let's see here. Let's just do one pin for right now. Alright, so we're going to turn the blue one on and off. So port F data, and we're going to bitwise OR it with blue. So blue, we're going to write a 1 to the blue pin, which was PF2, and then we're going to call our delay function, and then we're going to turn the LED back off, and then we're going to delay again, and we're just going to keep doing this over and over and over and over. So we're not using any kind of special like sleep, or I guess you could call it a sleep, but it's not like a defined function for a delay. It's just we're doing a software. We're just looping, doing nothing until it completes and comes back. So a lot of people don't like doing this in programs because it eats up the CPU processor time, but for this kind of example, it doesn't really matter. Alright, so this line here turns it off. And so exactly what is that doing? It's a bitwise AND with not blue. So it's going to invert all the bits of blue and it's going to AND it. And what that does is it basically gets rid of the ones in the blue position. And up here when we OR it, it's going to put the ones in. If you do the binary bitwise stuff by hand, it will make a lot more sense to you when you see it on paper. So I highly recommend just going through these lines by hand and writing out what the binary is for this variable, and it'll make a whole lot more sense to you. So I think we've got through all this, everything I need to talk about, and so now it's ready to upload to the board. So what we're going to do is I'm just going to save this to make sure that I don't lose anything, and then we're going to hit the little hammer here, and that's going to build it. Alright, we've build finished, no errors, we're good. Then come up here to the flash button, which is right next to the hammer, and we're going to hit flash. And my board is plugged into the USB of my computer, and I have the little switch connected to debug mode, and I'm going to hit the button, and it's going to flash this over to the board, and we should have a blinking LED, and we do. So you can play around with the delay count number here. This number here seems to be about half a second on, half a second off. You can play around with that, but hopefully this short video, well, maybe not so short now, but this video can describe to you how the memory addresses work. And see, the libraries, what they do is they do all this for you, so you can just call variable names and you don't have to figure out the addresses and the offsets and everything, but which is great if you already know what you're doing. But if you don't know what you're doing it the long way like this definitely helps you understand everything. And then later on you can just import the libraries, and you can do it a lot faster without so many lines of code. So I really hope this has helped you out. It helped me out a lot going through this, especially trying to make this as a tutorial that somebody else can follow. So we can put in some counts here in the delay function. So we can say we only want to blink 5 times. We can change which pin we want to, or which LED we want to blink, if we want to do the red one, the blue one, or the green one, or all three of them at the same time, which all it does is it flashes a white LED because they're all on at the same time. It looks white. You can also drive an LED that's not on your board. So you could use port A and look up its addresses and change these and actually do a jumper to a breadboard with an LED, and you can do it with an off-board LED. I did it with the onboard one just because it was easier to handle. I didn't have to do any jumpers. So that's it, guys. I hope that helps you.